Hi, this is another example for nozzle and diffusers. Instead of using the real substance such as steam or R134, and here we're using substance as ideal gas, so it's air. Okay, so giving a diffuser, and they want us to find mass flow rate and exit temperature T2. We immediately gonna thinking about our energy conservation equation, which will be H1 plus half V1 squared equal to H2 plus half V2 squared, right? So in order to solve that, we thinking about H1, H2. Another topic we need to quickly review to help us solving this problem is going to be delta H for ideal gas. Okay, so we learned about delta H for ideal gas. There are three different methods. The first one, you can use H2 minus H1 using table A17 for ideal gas table for air. Another one, delta H is going to be equal to Cp. That's right. If it's finding delta U, we would be using Cv, but for delta H, it's going to be constant pressure, Cp at 300 Kelvin, and then T2 minus T1. Or the third method we could be using is Cp at this average temperature, and then T2 minus T1. So for this problem, since we need to find the T2, and we really couldn't know the average temperature, right? So looks like this method is out. And however, we could potentially use either method 1 or 2 to figure this out. Maybe we'll try both, okay? So if we use method number 1, using table A17, so we need to find our H1 first. H1 at 10 degrees Celsius. 10 degree, that's going to be 283 Kelvin, right? And we're going to go to our temperature table. So let me quickly get mine out. And we said we're going to go to table A17. So scroll all the way down to table A17, our ideal gas table for air, and we're at the 283. So 283 is around, I'm sorry, 283. So it's between those two numbers. And look at it. At 280 is 280.13 and 285 is 285. So I can really estimate. So at 283, that would be around 283 for H. Do you agree? Okay. So that's going to be around 283. If you want to be exact, you can use linear interpolation. So it will be 283 kilojoule per kilogram. So we found our H1, then we just need to go ahead, go back to this governing equation to solve our H2. So plug it in for H1 is 283, and half V1 is 200 square. Then be aware, we're talking about the units before. This is in kilojoule per kilogram. So we really need times this 2000 times 1000 to get joule per kilogram, because half V1 squared we're talking about has a unit of joule per kilogram. So they will be consistent. So this will be in unit of joule per kilogram. Now that's going to be equal to H2, which we are solving, plus V2 is 0. Then we can figure out our H2 value. Okay. So put into calculator. And if we do that, our H2 is going to be unit of joule per kilogram. So it's 283,000 plus 200 squared divided by 2. That will give us about 303,000 joule per kilogram. So all those units is in joule per kilogram. But we really needed to change to kilojoule. So that's going to be 303 kilojoule per kilogram. That's our H2. So knowing H2, how can we find our T2, right? I think this is from my previous discussion. Okay, so then how do we, using H2, find our T2? We're going to go back to our table A17 again. See, at 303, what's going to be corresponding temperature? So let's go over here. At 303, so which is between, I'm actually looking at H value, right? H value is going to be 303, and what's going to be corresponding temperature? That is, again, estimate the temperature about between 300 and 305. That will be giving us 303. Around 303 Kelvin. Okay, so that's using the table A17, method number 1, we solved it. Using delta H for ideal gas. Now I'm going to try to use method number 2. So we're going to use CP at 300 Kelvin to approximate, right? So method 2 is more about estimate. Method 1 is more accurate because it's tabulated data. But now let's give a try using method number 2. Or step 5. So we have this H1 plus half V1 square equals H2 plus half V2 square. Then we'll have H2 minus H1. That's going to be our delta H, right? Then we'll have half V1 square. V1 is 200 minus V2, that's 0. So it will be that. And here we could use unit a different way because our half V1 square, we know it's going to be unit of joule per kilogram. How about we change this one to kilojoule per kilogram? So in order to do that, we're going to divide this by 1000. That will give us a unit of kilojoule per kilogram, and which this side is going to be kilojoule per kilogram. So let's go ahead and divide it for this particular method. So now we're going to find our H2 minus H1 is going to be equal to this 200 squared divided by 2, then divided by 1000. That will give us the number of 20 kilojoule per kilogram. All right, and since we're using method number 2, using 300 CP, specific heat at 300 Kelvin to approximate, and using T2 minus T1. Okay, and so let's go to look at CP at 300 Kelvin look like for the air. So that's from way beginning Okay, so we are here now. So we are from table A to A. And for air, and CP value is 1.005 right here, right? So 1.005, that's from our table A to A. So knowing that, and the unit for CP specific heat is kilojoule per kilogram per Kelvin, and T2, that's what we are solving. T1, that is 10 degree. So since it's temperature difference, I don't need to change this to Kelvin, right? Because this will already giving us Kelvin. Delta T in degrees Celsius is going to be equal to delta T in Kelvin. Okay, so knowing that, all those together give us 20, right? That's our H2 minus H1. Then let's go ahead and solve this. T2 minus 10 degree, that will give us 20 over 1.005. That's 19.9. So then we can find our T2. That will be 10 plus 19.9. That will be 29.9. And the unit will be, since this is using degrees Celsius, so this will be in degrees Celsius. Then if we were about to change that to Kelvin, we're going to add 273. That will be around 303 Kelvin. Is that cool? Because you got the same answer as the other method. Okay, so now you figure out your T2, but we still need to figure out one more unknown, which is mass flow rate. Let's go back to thinking about how do we solve mass flow rate. We have a formula for mass flow rate, which is volume flow rate divided by specific volume. If we are looking at inlet, so we're going to add a subscript 1, right? So the volume flow rate has a formula that's going to be velocity times cross-section area. And specific volume, we need to find out specific volume, and this is ideal gas. So we're gonna thinking about what is ideal gas equation, right? If it's ideal gas, that will be equal to P small v equal to RT, and we're going to add subscript state 1, which is inlet. So specific volume for inlet is going to be equal to RT1 over pressure. Now let's take a look. R for ideal gas, it's 0.287 kilojoule per kilogram per Kelvin. And T1 is 10 degree. Change that to absolute Kelvin. So that will be 283 Kelvin. Then the pressure is in 80 kilopascal. So we divide it by 80 kilopascal. Kelvin cancel out. And kilojoule divided by kilopascal give us volume. So that we will get meter cube per kilogram. That is our specific volume unit. And now let's go ahead and put our values in. 0.287 times 283, then divided by 80. That gives us 1.015. That's our specific volume. So knowing this, we'll see, okay, we'll go back to put into our equation 6 here for mass flow rate. So mass flow rate is going to be equal to velocity. We do know velocity for this problem is 200 meters per second. We also know cross-section area. So velocity 200 meters per second, then times 0.4 meters squared for cross-section area, then divide by specific volume. You just calculate in step 7 using ideal gas, 1.015 meter cube per kilogram. Then we got our ideal gas unit, mass flow rate unit, so which is kilogram per second. Now let's put our values in. So it's 200 times 0.4 divided by 1.015. 0.015. That will give us 78.8 kilogram per second. All right, so I think we complete this problem, and this is a good problem. Why so? Because it's a diffuser problem, first of all, and also, since it's ideal gas, we used this old topic of delta H for ideal gas, and we're talking about there are 3 different methods, and here we use 2 different methods: ideal gas table A17 and using 300 specific heat CP to calculate. We get the same results. Okay, and also this problem help us review the mass flow rate concept and the volume flow rate concept once again. Alright, so that's all for this video. I'll see you next time.